it's about 2 minutes after the hour, so I think that we can get started. But hi, everyone. Welcome back to the second session of the Electrochemical Impedance Spectroscopy webinar. My name is Rosie Ray. I'm an application scientist with NeuroNexus, and yeah, we're super excited for this webinar today. So NeuroNexus is a leading producer of electrophysiology instruments and software for neuroscience, and so much of what we do is grounded in electrochemical impedance spectroscopy. The deep understanding and foundational knowledge completely allows us to do what we do. And that's why we're especially excited to continue this series today. I would like to thank our co-sponsors, the International Society of Electrochemistry and the Electrochemical Society, for their support in making this series possible. And of course, a special thanks to our speaker today, Professor Mark Orazem, who you will get to hear more from him and about him in just a minute. And I want to give a special thanks to everyone that's here. The last session last week, we had 700 attendees, absolutely amazing, really great interest in this topic. And we are just excited to continue this series. And so with that, I'm happy to introduce the founder and the CEO of NeuroNexus, Dr. Daryl Kipke.
Thanks, Rosie. NeuroNexus is pleased to have the opportunity again to host and produce this important three-part webinar series. And I have the great honor of introducing our speaker, Professor Mark Orazem. Professor Orazem is a world-renowned expert on electrochemical impedance spectroscopy. He is a distinguished professor of chemical engineering, the William P. and Tracy Cirioli Professor of Chemical Engineering, and associate chair for graduate studies at the University of Florida. Professor Orazem has received many awards for his outstanding scholarship and is a fellow of the Electrochemical Society, the International Society of Electrochemistry, and the American Association for the Advancement of Science. In addition to his extensive list of research publications, Professor Orazem is the author, along with Bernard Triboulet, of the definitive textbook on impedance spectroscopy, aptly named Electrochemical Impedance Spectroscopy, now in its second edition. Mark, welcome again, and we look forward to your talk.
Thank you, Daryl. Appreciate being here. Thank you, everyone, for being here. The topic for today is interpretation, measurement, and analysis of electrochemical impedance spectroscopy. And just like before, I want to thank our co-sponsors for this, the Electrochemical Society, the International Society of Electrochemistry, and also NeuroNexus, who is hosting this event. And I also point out that this series of webinars is a deliverable from the research project that we have funded by NIH on engineering the neuronal response to electrical microstimulation. Kevin Otto is the MPI along with me. And then we have Duke, Dallas, UT Dallas, and NeuroNexus listed as participating companies and universities. In this series, we began on April 1st with just an introduction to impedance spectroscopy. And then today, what I want to talk about is interpretation, measurement, and analysis. And then on the 15th, we will go to application to neural engineering. And I want to emphasize that impedance spectroscopy is of interest to many, many people working in different areas. And even though what we covered on the 1st and today is general, it will be of interest to people interested in neural engineering. And even though what we cover on April 15th will be dedicated to our electrodes for neural devices, it would still be of use to people who are studying other things like batteries, fuel cells, corrosion. Now, in the advertisement, I should go back here. So on April 8th, today we will cover measurement, model development, and then also a graphical analysis. So we'll focus on how we can use graphs to interpret our results. And in the advertising flyer for this, we use this image, and I want to explain what this image is all about. Those who have worked with me know that I am not very fond of graphical abstracts. But Vincent Vivier and I published a paper in Chemical Reviews, and a graphical abstract was a requirement. So this is the image we came up with. And the hand with the pencil is actually the hand of Vincent Vivier. It's been obviously altered a bit. And then the impedance diagram is some of our impedance data. And the hand is basically trying to model the impedance data. And we're thinking in terms of an inductive loop. And so we're thinking in terms of electrochemical reactions that are coupled by an adsorbed intermediate. And I learned to draw the elephant using directions I found on the internet. And so I drew the elephant, and the elephant is there to remind us, in the spirit of the old Buddhist tradition of the blind man and the elephant, that whatever model we develop is not guaranteed to be the correct model. The model that we develop is not unique. And other mechanisms maybe would be the appropriate way to model this thing. So that was my attempt at making a graphical abstract that actually said more than just a picture. So today, I'd like to begin with talking about measurement techniques. The AC bridge we talked about a little bit last week. Lissajous analysis, I'll mention this a little bit more in detail a little bit later. Hawking amplifiers or phase-sensitive detection is also used. And then most of the instruments that I've worked with use a Fourier analysis. And so this can be done in different ways, but typically I'm working with a digital transfer function analyzer. And so the way we'll just focus on that one, and the way it works, if we imagine that we have a potential and current signal given in terms of a magnitude times the cosine of omega t. Omega is the angular frequency. Consider that to be the input. Then the output would be the magnitude of the current times the cosine of omega t plus a phase lag. And so we can use an integral over time, over an integer number of cycles, multiplying, let's say, the current times the cosine, or, let me find my mouse, there we are, or the current times the sine, giving me in-phase and out-of-phase behavior, and express this now in terms of frequency-dependent complex numbers. And we can do the same thing for the potential, the in-phase part and the out-of-phase part. Again, integrating over an integer number of cycles. And then the impedance we calculate is simply obtained from the real and imaginary parts of the ratio of these two complex numbers. So this is, we'll talk a little bit more about that later, but anyway, that's the basic idea of how the Fourier analysis works. For experimental considerations, the electrode dimension is one of the things we might want to talk about. Another is the frequency range. It's typical that we think of the frequency range as being the range of whatever instrument we purchased, but really the system we're trying to study controls what frequency range is relevant. And so instrument artifacts will control perhaps the high frequency end. Non-stationary behavior would control what would be the lowest frequency you can measure, and you're still wanting to capture the system response. The second issue that we could talk about is linearity. And in the work that I'm presenting here, I'm going to be focusing on small perturbation amplitudes. So I would like this system to have a linear or pseudo-linear response. So this means a small perturbation amplitude. But what constitutes a small perturbation amplitude depends very much on the polarization curve for the system under study. And it's something that we have to determine experimentally. Another issue is the noise level of the measurement. The smaller you make the noise level of the impedance measurement, the more easy it is to establish or to do a regression to get information about the system under study. So one of the things for any of you who are graduate students in this audience, this is a really fun thing to do. You can calculate what the impedance response would be. I did this in MATLAB. Basically, I have a potential perturbation, which is a steady value of the potential plus a delta V in magnitude times the cosine of omega t. And then we calculate the current, and here I'm using a TOEFL expression, which basically says that the current is given by a rate constant times the exponential of a constant times that potential. And so this exponential is what gives rise to nonlinear behavior. The charging current is the capacitance times dV dt. And since you take the derivative of potential, we find that this current is going to be exactly out of phase with the incoming potential. whereas the Faradaic current, the current that we're getting from this exponential, is going to be in phase. And so V is the potential basically driving the reaction. I'm not including an ohmic resistance in this calculation simply because it makes life easier to do that. And then when you calculate, here I'm calculating sort of a normalized current and a normalized potential so that both signals go from -1 to +1 as a function of time. You see that at very low frequency, the two are very much superposed. The reason for that is that the charging current does not play a major role at low frequency. We're seeing primarily the Faradaic current. And then as you go to higher frequency, we begin seeing a phase shift. The phase shift occurs because at higher frequencies, the charging current is starting to play a role. So at 100 hertz, which is sort of like characteristic frequency for the system, we're seeing that the charging current and the Faradaic current are playing roughly equal roles. If we go to still higher frequency, the phase shift increases, and now we're seeing that it's mostly charging current that we're seeing, very little Faradaic current. One way of looking at this, instead of looking at the signals as a function of time, is to look at a Lissajous plot. So here I'm plotting the current versus potential, again scaled. So I'm going from -1 to +1 for current and -1 to +1 for potential. And what we're seeing is that at low frequency, we see a straight line. At higher frequencies, we see an ellipse. And then at very high frequencies, we see a circle. And the reason we're seeing a circle there is because there is no ohmic resistance. If there was an ohmic resistance present in the calculation, we would see another straight line at very high frequency. But this Lissajous plot is really a way that people use to measure impedance. And I like to talk about this. You can imagine, this is the day before digital cameras. So you would have a camera on a tripod, and you'd be basically training the camera onto an oscilloscope. And at low frequency, you know that the oscilloscope is just showing you a dot that moves slowly around the screen. So what you need is a long exposure time for the picture that you will take. So for every frequency, what you would do is take a photograph of the oscilloscope, and then you would develop the picture, make a print, and then you could use a ruler to measure the impedance. So the magnitude of impedance would be given by the maximum difference in the current, let's do a maximum difference in potential going from the origin to A, divided by the maximum difference going from the origin to B. And that would give you the magnitude of the impedance. And for the phase angle, it'd be the inverse sine of minus the ratio from the origin to where this signal crosses over the axis here, and the origin to the maximum point A. So this is the way that you would make an impedance measurement in the old days. One of the ways that you do it in the old days. And you would do this for every frequency. We are spoiled. We have instruments that will do all of this for us. One of the things I wanted to talk to you about is the effect of nonlinearity. So if you use a larger perturbation amplitude, then that exponential in the expression for the Faradaic current starts playing a role. And what we're seeing here is, again, using the same normalized current and potential, we're seeing that this is the potential and the current is now shifted. And just simply because of, the large perturbation amplitude that we're using. What's happening at very low frequency with a large perturbation amplitude is that you're literally tracing the current voltage curve, the steady state polarization curve. And so that will give rise to a change in the behavior of the current with time. And we see that shift becomes smaller as we go to higher frequency, and that shift disappears entirely when you go to even higher frequency, because at this point, we're seeing only the charging current. The Faradaic current plays no role, and the effect of nonlinearity is gone. I love looking at plots like this. In the Lissajous figure, what you're seeing is that at very low frequency, instead of seeing a straight line, we start seeing a line that is distorted. And if we look at a slightly higher frequency, then we start talking about fruit. it looks like a banana instead of looking like an ellipse. At still higher frequency, maybe I have to talk about eggplants, but basically you end up with a distortion again in the Lissajous figure. And then again, at very high frequency, because there's no ohmic resistance in this figure, then we end up with a circle because all we're seeing here is the charging current. So if you have a storage oscilloscope, or if you have an instrument that shows you the Lissajous figure as you're making the measurement, this becomes a very nice way to know, kind of like instantaneously, whether the perturbation amplitude that you're using is too large. If you do not see a nice ellipse in the Lissajous figure, if you're seeing it distorted, then you know that you have a nonlinear behavior. There are other ways of doing that. If you look at nonlinear, if you're using large perturbation amplitude, you will see non-zero values for the harmonics. You can calculate a total harmonic distortion. That would be as a function of frequency. There are other ways of checking out experimentally whether your perturbation amplitude is too large. But the point is that it really is something that is dictated by the system that you're trying to study, and frankly, also by the frequency range. There is a change in the answer that you get for the impedance. So here, the line represents what we should get. With a very small perturbation amplitude, the symbols overlap with that line. But as you go to larger perturbation amplitudes, and these are all calculations, then we see that there is a distortion. And this is one way that people use to check whether the perturbation amplitude was too large, by making measurements over and over again with changing perturbation amplitudes, seeing the point at which the impedance starts to change. So that, yeah, I realized I'm going through a lot of things relatively quick, and maybe we can cover things with questions afterwards. The next thing I want to talk about is the accuracy contour plot. And these are measurements that we collected using the Gamma reference 3000. And so this is something that you can measure, and really honestly should measure. One point is you measure a shorted measurement. So you're basically connecting the electrodes together. What you want to do is not to connect them using alligator clips, because alligator clips have an impedance on the order of about a milliohm already. So what you want to do, what we did is we used a copper block and we drilled holes in it to accommodate the banana plugs, and then we were able to put the connections through that. Another approach that the Gamma people recommend is to use kind of like a copper mesh, a copper fabric, and then use the banana plug, or use the alligator clips connected to that, so you have lots and lots of contact area. So that's one thing you do. The second thing you do is measure at open circuit. And so the shorted measurement is done under galvanostatic modulation. The open circuit measurement is done under potentiostatic modulation. And we don't add a resistor or capacitor. We just have the wires that are not touching each other. We're measuring really the impedance of the wires. And then these measurements that I'll show you were performed in triplicate. We used the measurement model to assess the error structure, and we used the high accuracy setting on the instrument. And this is what we got. So there are three measurements that overlap nicely. Over here, this is the high impedance part, and the stars represent the noise level of the measurement. And we see this line here represents the capacitance of the wires. Down below, this is for the shorted measurement. We're seeing that at low frequency, we get down to around 1 microohm. And then the stars again represents the noise in that measurement. You're also seeing, as you go to higher frequency, that you start seeing the line increase. This is where you're starting to see the inductance of the leads. So I was asked a question last week by someone who was working on a coated electrode, and he was saying that the person asking the question was saying that they were unable to really get a steady state potential, an open circuit potential. And the question was, how do you make the impedance measurement? And my answer was not complete and a little bit misleading. What I'd like to do is modify the answer here to say that it's very likely that when you're making measurements with that system, that your impedance will be sufficiently large that you'll be seeing simply the impedance of the leads. And this is something that we'll be talking more about next week, because our group is working with ultra micro electrodes. Ultra micro electrodes are very high impedance electrodes. And it is very possible for us to be in a situation where the impedance of the electrode is high enough that what we are really seeing is just simply the impedance of the wires and not the electrode itself. So that you should be aware of this. And also, while this analysis is fine if you're using the cables that came with the instrument, if you're going to have, like we do with our ultra micro electrodes, we have some kind of a junction box that we have to use to connect the instrument to the device. And that junction box has a capacitance associated with it itself. And so what that means is that this line, instead of being up here, ends up moving down. And so it is to your advantage to know what your accuracy contour plot is for the system that you are studying. Like I said, we'll see more of that next week. Other things to talk about, one is cell design. We use the reference electrode to isolate the influence of electrodes and membranes. So if you have a 2-electrode measurement, which quite frankly often is what we have to do, we have to be aware that we are measuring the current between the working electrode and the counter electrode. And we are also measuring the potential difference between the working and the counter electrode. What that's telling us is that the impedance that we measure includes the impedance of the working electrode, the impedance of the counter electrode, and then the impedance or the electrolyte resistance of everything that's in between. So if we want to isolate the working electrode from the counter, we could introduce a reference. And this is typically done. The current ends up being the same as it was before because the current is flowing between the working and the counter, but having the reference here allows the potential to be in between the working and the reference. And so our impedance then will be the impedance of the working electrode, and then the difference, the resistance between the working electrode and the reference. If you're studying membranes, so in the days when we were looking at human skin, for example, cadaver skin, we would have a cell set up so that we could put the skin in between two chambers. There we were not interested in the impedance of the working or the counter. We were interested in the impedance response of the skin. So we used 2 reference electrodes to measure the potential difference. Another issue about electrode design is the issue of the current distribution. And here what I'd like to focus on is the primary current distribution, which is governed by the ohmic resistance of the electrolyte and the geometry of your electrode. I'm told that this is very old-fashioned. This is the way I was taught electrochemical engineering: the primary current distribution, secondary, tertiary. The primary current distribution is simply governed by the ohmic properties of the electrolyte and the electrode geometry. So this line here, the black line represents the electrode. The blue line represents an insulator. The electrolyte is everything in between. So if we have an angle between the electrode and the insulator, then this angle is less than 90 degrees, and the current density at this interface, at the junction of the electrode and insulator, wants to go to 0. I find this way of looking at this very useful. If we have a 90-degree angle, then the current tends toward being uniform at the junction between the electrode and the insulator. If we have a larger than 90-degree angle here, like 180 degrees, which I'm trying to represent here, then the current at this interface tends toward infinity. So this is actually very useful because you can just look at the geometry of your cell and know whether the current distribution is likely to be uniform or not. Fortunately, in almost all the cells I've ever worked with, I've had a non-uniform current distribution. For example, if I'm using a rotating disc electrode, so here is a cross-section showing the electrode and the insulator, then what you're seeing is an angle that is greater than 90 degrees between the electrode and the insulator. Here's a picture of one, and you would see that this would give me a non-uniform primary current distribution. If you were, however, going to make this insulator such that the electrode is recessed, then this recessed electrode has a 90-degree angle between the electrode and the insulator. If this depth is sufficient, like twice the diameter of the electrode, then the current distribution will be uniform. If we have a spherical electrode, if you can ignore however you make electrical contact to the electrode, then you will have a uniform current distribution, and the hemispherical electrode takes advantage of this, basically bisecting the electrode at the midsection here. And so this will give you a 90-degree angle at the junction between the electrode and the insulator. So these hemispherical electrodes are often used in situations where you want to have a uniform primary current distribution. Now, why do I care about this? What happens is that above a certain frequency, if we have a non-uniform current distribution, that affects the impedance response. And that can influence your ability to interpret your data. So, here's a picture of a hemispherical electrode. So what you find is that frequency is, the characteristic frequency is 1 over 2 pi times the ohmic resistance times the capacitance. We will make use of this next week when we talk about the Syroff electrodes. Okay, so you know how to tell whether your electrodes have a uniform and non-uniform current distribution. If you're like me, almost all of your electrodes are non-uniform, so you have to deal with that. Other issue, we want to reduce the stochastic noise. So if you want to reduce the noise of your measurement, make sure the current range that you're using is correct. In the old days, when I was first learning impedance spectroscopy, I was able to change the current range once in the course of a measurement. So it was very likely to be making a measurement with a suboptimal current range. With modern instrumentation, it automatically changes from the current range to current range as necessary as the impedance changes. So this is not such an issue as we normally have. The other issue is integration time. You saw that in the Fourier analysis approach, we're integrating over an integer number of cycles. The larger the number of cycles you're integrating over, the smaller the noise of the measurement will be. In the old days, we were using a Solitron frequency response analyzer, and they had an automatic integration feature that would allow you to automatically integrate until you reach some kind of a closure error, and then you'd move to the next frequency. With the Gamma instrument, you have something like fast, normal, and low noise as the options that you would choose. But effectively, in this case, it's the instrument provider that is making this decision as to how many cycles to use. Another issue is delay time, and this is normally handled directly by the instrument providers these days. But basically, when you switch from one frequency to another, there is a transient response, and you don't want to include that transient response in the integration procedure. So there's usually some little bit of a delay before you start making the impedance measurement. So again, when I was first learning impedance, I controlled that completely. These days, that's managed by whoever sold you the instrument. Another point is to avoid the frequency at which you receive electrical current, the line frequency and the first harmonic. I wrote here plus or minus 3 hertz, 5 hertz, but currently I'm using plus or minus 3 hertz, and that works just fine. So in the US, what this means is that you try to stay away from 60 hertz and 120 hertz. If you're in Europe, you stay away from 50 hertz and 100. What's going to happen is that when we analyze the impedance data, if you use our measurement model program, we literally get rid of any data points that are within this range. 60 hertz plus or minus 3 or 120 hertz plus or minus 3. Because no matter how good the instruments are, there's enough noise coming from the line that it just can't quite get rid of all that noise. And it gives you a little bit of a bump in your impedance that maybe isn't so visible if you look at a Nyquist plot or a Bode plot. But when you start doing regression analysis, it starts affecting your ability to extract information. On a similar vein, whenever I'm doing regression analysis, I ignore the first frequency measured, because going from a steady state to 100 kilohertz, that requires a larger delay time than what the instrument vendors provide. And the easiest way to get around that is just to delete that first frequency measured. It does this, again, you'll see that effect when we talk about this stuff next week. To reduce non-stationary effects, just make the measurement faster. But it's a question of trade-offs, right? If you reduce the time for the measurement by, let's say, making each frequency measurement faster, you're accepting more stochastic error to get less bias error. Or if you say, I'm just going to measure fewer frequencies, the more measured frequencies you have, the better your parameter estimates will be. But measuring fewer frequencies takes less time. It's always a balancing act. Again, stay away from the line frequency. If you're using any kind of auto integration feature, you will take the maximum amount of time to make the measurement at the line frequency, and then you're going to throw away the measurement anyway. So you don't want to do this at all. So carefully design your protocol to avoid the frequency at which you get electrical current. You can also select the appropriate modulation technique, decide what you want to hold constant. System drift can increase the measurement time. So you may want, if you're trying to make measurements at open circuit, you may want to control current instead of potential. About bias errors. Okay, buy a better potential stat. Okay, that'd be good. Use short leads, shielded, twisted leads. Use a Faraday cage if your current is small. So for our ultramicroelectrode studies, we use a Faraday cage to eliminate or to reduce the influence of other external electric fields. One of the issues we learned about more recently is that the current range itself has a given bandwidth. That bandwidth of the current range is affected by the capacitance of the leads. And so if, like we had in our case, we are connecting the wires from the leads from the instrument to some kind of a junction box which has its own wires, therefore its own capacitance, that changed the bandwidth that was usable for the current range. And so we had to basically limit that bandwidth, effectively trading off using a suboptimal bandwidth for having a bandwidth that did not cause some kind of a bias error. And then the other thing I've learned is that it's really useful to check results against this electrical circuit. One example I can give you is, we're talking about early days when I really did not understand the accuracy contour plot. I was asked by one of my colleagues to look over an experiment he was measuring. And he was making a measurement in a glove box. The glove box, it was in one part of the room. The instrument was in another part of the room. There was something like a 20-meter cable connecting the instrument to the system that was being studied in the glove box. And they were seeing an extra little capacitive loop at high frequency that no one else had reported. And so before writing a paper on it, I was asked for my opinion. And so I asked them to just simply build an electrical circuit using a breadboard and resistors and capacitors that would give roughly the same impedance they're seeing, and put it inside something that they knew would give you one capacitive loop. And they put this inside the glove box, made the measurement, and they saw that, again, they were seeing two capacitive loops. That one capacitive loop was simply due to the capacitance of the wire. The longer the wire, the larger the capacitance. You can also check against independently obtained parameters like the ohmic resistance. Gives you information. If you have a well-defined geometry, then if you know the conductivity of the electrolyte, then you know what the ohmic resistance should be. And then again, check the results against the accuracy contour plot. If you're making measurements for very high impedance systems, you should know what the accuracy contour plot is for your system, so you know at which point you are simply measuring your wires and not measuring your system. One last question about measurements is, can we perform impedance on transient systems? And the answer to that really depends on the time frame for your measurement. I mean, there's a certain amount of time required to make a measurement at each frequency if you're doing one frequency at a time. If the system is changing so fast that it's changing within this window, then impedance spectroscopy is not an option for you. If the system is changing so that it's changing such that it gives you, it's not changing for an individual scan, but it's changing over multiple scans, now impedance spectroscopy becomes a very powerful tool. But, basically it could be the situation where, over multiple scans, the system is changing, but for each individual scan, we may find that we're able to get Kramers-Kronig consistent results, but only if we delete the low frequency data. So the Kramers-Kronig relations ends up being your friend here, allowing you to know what part of the measurement is going to be useful to you. And here I'm showing you, this is again with the Solitron instrument, showing you the amount of time required for each measurement at each frequency. And what we're seeing is that at low frequency, it takes about 3 cycles to get a measurement. And so the time required at low frequency is much larger than the time required at high frequency. At high frequency, here we're seeing about 5 seconds, simply because as you go to higher and higher frequency, there's more noise, and it takes more cycles to filter out that noise. So I like this plot because it gives me a sense for really the balancing act that you're taking. More time for measurements at low frequency, less time at high frequency, but it's not like at high frequency it's instantaneous. There's still a certain amount of time required. So, okay, that was my very, very quick rush into some of the things to think about making your experiments. And if I did not capture what you're concerned about, put it into the questions and we'll deal with it later. What I'd like to do next is talk a little bit of how we develop process models. And we use electrical circuits to guide, basically to create a framework for the model. And then we use a phasor approach to calculate the Faradaic contribution. So what we're talking about here are the concepts of voltage addition and current addition. So if we're looking at voltage addition, what we're seeing here is a diagram that shows a potential drop across the electrolyte and then a potential drop across the interface. So if we have addition of potentials across the electrolyte and across the interface, that means these impedances are in series. So that's the way we would build this if we were talking about addition of potential. If we're talking about addition of current, so for example, let's focus in on this interface, and we'll say that at this interface, we have 2 kinds of current, a charging current and a Faradaic current. Since those currents are being added together, the corresponding impedances are in parallel. So this is how we end up with a capacitance for the charging current in parallel to this box for the Faradaic current. And so, we could see something, typical circuit like this. I'm using a box for the Faradaic impedance because I want to deal with how to calculate that or derive that next. Now, these are very simple concepts, but I find them to be very powerful. So for example, if you're making measurements in open circuit, which is very, very commonly done in corrosion. So call that the corrosion potential. Then at the corrosion potential, we have 3 currents that are happening on the surface that are being added together. You have a charging current. You have a current associated with the anodic reaction. And you have a current associated with the cathodic reaction. And yes, the total current is equal to 0, but that's simply because these 2 currents cancel each other out. But the impedances associated with those currents still have to exist. And so those impedances are going to be in parallel to the impedance associated with the charging current, which is shown here as a capacitor. So The question you might ask if you're studying corrosion is, do I really have to do all of this? And one way of checking that is to make measurements not only at open circuit, but at plus or minus some small amount. Here I'm showing plus or minus 10 millivolts, reference to open circuit. And what we're seeing here in these results, and this is for steel in some kind of saline solution, but basically we have an open circuit potential here, which is the squares. Then we have an open circuit minus 10 millivolts, which is the blue circles, and then open circuit plus 10 millivolts, which is the red triangles. And what we're seeing is that the impedance gets smaller when we go both plus and both minus. So what that's telling us, and here, this is from our book, but this is showing you that if the impedance decreases when you go plus delta V, and it decreases when you go minus delta V, that means that we need to consider both anodic and cathodic regimes. If the behavior was different, as is shown in this table, then we could ignore one of these. If ZC is much larger than ZA, then that would mean that the current doesn't flow through ZC. It flows through ZA. So that means that ZC would not be involved in the measurement. It doesn't mean that cathodic current does not happen. It means that we don't see it in the impedance response. So it simplifies the model we have to develop. I'd like to think a little bit about a partially blocked electrode. So let's imagine we have a very thin dielectric that partially covers the electrode surface. So in this particular case, there is a charging current that goes through this dielectric. There's a capacitance basically that defines the behavior of this dielectric material. In addition, you have a charging current associated with the bare metal, and you have a Faradaic impedance, which is where the electrochemical reaction is taking place. So we're assuming that this layer blocks any kind of steady state current. All we see is the charging current. And gamma represents the fractional coverage of the surface with this material. So 1 minus gamma is the bare material. So we show here a mathematical expression for the impedance. Now, one thing that's kind of interesting is that we can use this to learn how to look at impedance data. So for example, let's say that the ZF that I showed you before is just a charge transfer resistance for a simple electrochemical reaction. Then this is our expression for our impedance in terms of RTs instead of ZFs over here. So if we look at the Nyquist plot, then what we're seeing is that as the coverage of the surface decreases, let me put it this way. As the coverage increases, so this is gamma equal to 0.9, means the impedance becomes really large. And the impedance can become smaller as we have more bare electrode surface for the parameters I've chosen. So one thing that's kind of interesting is that what's different between each of these curves is simply the fractional coverage of the surface by this blocking layer. The shape of the curves stays pretty much the same. And so what we can do here is to calculate a normalized impedance, where I'm taking ZR, the real impedance minus the ohmic resistance, and dividing that by the value at zero frequency, which is this point over here, minus RE. So that gives me a number that goes from 0 to 1. And then we scale the imaginary part, just simply scaling by the same thing that we scaled the real part by. It's just the imaginary part divided by ZR at 0 minus RE. And what you see is that all these points superpose. You also see that the symbols are not superposed. So what that means is that this superposition is seen in a Nyquist plot, but not if we plot the real part versus frequency or the imaginary part versus frequency. But this thing is actually going to be used later on in this presentation. I'll show you how we make use of that concept. But the idea is that because the electrochemistry did not change, the only thing that changed was the fractional coverage of the surface, then those Nyquist plots superposed. If that layer becomes thicker, then we have to consider the resistance of the electrolyte in the pore. So we go back to voltage addition or potential addition. So we have a voltage drop across the electrolyte outside this material. We have a voltage drop through the pore, and then we have a potential drop at the electrode surface. And so that changes the nature of the circuit is shown here. It changes the nature just simply by introducing this ohmic resistance inside the pore. And very often for electrochemical systems, we'll see a thick dielectric, but we will also see a layer outside. So an outer porous layer and an inner dielectric. So this porous layer allows current to flow. So there is a resistance going through that. And then here for a thick layer, we still see the resistance associated with the pore. And then again at the electrode surface, at the bare metal surface, not covered by the dielectric, you have a charging current and you have a Faradaic current. And once again, we're representing the Faradaic current or Faradaic impedance just by this box. So this becomes similar to what we would see in the previous one, but basically with this extra term here, which corresponds to the impedance of this outer porous layer. One thing that's really kind of fun about this is that the impedance of this outer porous layer that has a characteristic time constant, the R times C. But the capacitance is given by a dielectric constant times the permittivity of vacuum divided by the thickness of this layer. The resistance is given by the thickness of the layer divided by the conductivity of the layer. If you multiply R times C, the deltas cancel. So what that means is that this time constant is independent of the thickness of the film. And it's not uncommon for this time constant to correspond to a frequency that's outside the measured frequency range. So if this is outside the measured frequency range, then this term here will appear to you as if it was an ohmic resistance. You will see Re plus this resistance of the film. But the resistance of the film will be changing as the thickness of the layer increases. So I have one experiment that was done by my collaborator, Bernard Triboulet, with his colleagues in Tunisia. And what you're seeing here is the measurement where we're plotting the apparent ohmic resistance as a function of time. And he's seeing here that this ohmic resistance is changing, increasing with time, in spite of the fact that the electrolyte is not changing. There should be no reason for this to happen. So they very tentatively washed the electrode surface with a squeeze bottle and saw a small decrease. So they were more vigorously washed this, and they saw that the resistance went down. And then as time increased, the resistance increased, and then they washed it again and it went down. This is an example of a case where you see this type of, you see that this loop, this RC couple exists, but cannot be seen. And that's the reason I use dashed lines for the capacitive part. All you see is the real part. Second. So what we're saying here is that if we're looking at an Nyquist plot, and I'm terrible at writing with my mouse, but I'm looking at the imaginary minus the imaginary part versus the real part. What we're saying is if the maximum frequency I can go to is, let's say right here, then even though this loop exists, all we will see is this real part here connected to the ohmic resistance. So this will be Re plus the resistance of that layer. And I'm going to erase this as fast as I can. Okay, so we've used circuits to help create a framework, and I've used boxes to say this is where the Faradaic impedance goes. I'd like to show how we calculate a Faradaic impedance. And okay, so the Faradaic impedance, here's the Faradaic current, which we're saying in general its case is a function of potential, concentration of the electrode surface, and gamma. And we're going to express that in terms of a phasor. So we have IF bar, which is the steady state value, and the real part of the current phasor times the exponential of j omega t. And so we can calculate what this phasor is using a Taylor series expansion, ignoring all higher order terms. So we just simply take the derivative of this function with respect to potential and then multiply by a v tilde, the potential phasor, holding everything else constant. Do the same thing with respect to concentration, do the same thing with respect to the fractional coverage of the surface. And so I'm just going to show a very simple case where we have this is an expression for the current in terms of the number of electrons transferred, the Faraday's constant, a rate constant. We like to just simply lump all those terms, call this K. This constant here has units of current density. And then we have the exponential of the B, which this B represents the apparent transfer coefficient, Faraday's constant over RT. We take the derivative of this expression with respect to potential, and we end up with this K multiplied by this B, and then times the exponential at the steady value of potential. All of this now multiplied by the potential phasor, which can also be expressed as 1 over a charge transfer resistance versus times this phasor. This RT is shown here to be 1 over this KB times this exponential of B times B bar. And we can express this in terms of TOEFL slopes. So this is 2.303 over B. And this K times this exponential is the steady state current. So what we're saying is that we now have a relationship between the steady state current, the charge transfer resistance that we calculate, and the TOEFL slope. So you can, for example, calculate the TOEFL slope using this and do this at different potentials. This TOEFL slope should be independent of the potential. So if it is, then that gives you some confidence that you're on the right track with your model. And if it is not, it's suggesting that your model is not sufficiently complex, that you need more things in it. So circuits provide the framework, and the reaction mechanism provides the Faradaic impedance. So if this is the framework we created, then this current is given in terms of this derivative of this current phasor is given in terms of the derivative of the steady current with respect to potential. And that gives me eventually a Faradaic impedance that's just simply a charge transfer resistance. So, I mean, this is what you would know, that if you have a simple electrochemical reaction, the Faradaic impedance can be expressed as a charge transfer resistance. The advantage of everything we've gone through is you know what this parameter means. Now, I misjudged time. So I'm seeing that it is getting close to 1 o'clock. I wanted to give enough time to answer questions. I have a little bit more to cover over here, but maybe I should add that to the next presentation. Rosie, what do you say?
Yes, we are getting close to time, and there are so many good questions already that have been submitted. And so maybe we can pull whatever else you have over into the next session next week, if that sounds good to you.
That sounds good to me.
All right. Well, thank you for that amazing lecture. I know for me that added a lot of context to the application of this topic, and so I thoroughly enjoyed it. And yes, we have plenty of questions that have been asked. One of the ones I do want to address before we get into the nitty-gritty of it, a lot of people were asking how to access the recordings of last week's session and this session. The recording from last week is uploaded on our Spotify and our YouTube. I put links for those in the chat, and so everyone can go and see that. And then the recording of this session will be uploaded later today on those platforms, so just keep an eye out for that. And so getting into some of these questions. So someone asks, hi, why we measure EIS from high to low frequency and how temperature can affect this. One more is, please, a little bit explain potentiostat EIS and galvanostatic EIS.
Okay. Two good questions. And also I'll point out that if you go to my website, I also have a link in my video room to the presentation from last week. Okay, the reason I like to go from high to low frequency, and really a lot depends on what you're trying to do. but typically I have a good idea for what the ohmic resistance is. So I know what parameters to use at the beginning of the measurement at high frequency. So going to high frequency to low kind of makes sense to me on that level. The other approach is if you have a somewhat non-stationary behavior, the high frequency measurements are really fast to do. And so, if you have something that's changing such a way that, the first few minutes of your measurement will be okay, but by the time you get to the third minute of measuring, you're affected by the non-stationary behavior, then you'll be seeing that the low frequency measurements take longer. And so you'll be seeing the effect of non-stationary behavior there, and you'll be able to get more frequencies before that starts kicking in, basically. For some measurements, I've used just the opposite. So it is somewhat system dependent, but for right now, let's say that's what we're doing. Potential static means we're controlling potential. So basically the way the instrument would work is that you say you want to make a measurement at a given potential, you let it sit at that potential for a period of time, and then what you'll do is hold the potential at that value, and you'll add to that a modulated or sinusoid in potential. The advantage of potential static is that linearity is controlled by potential, not by current. So the perturbation amplitude can be chosen to give you a linear behavior throughout the frequency range. Galvanostatic means we are controlling current. So the way the system would operate is that you would tell it what current you want to measure at, and it would hold the current at that value, and then you would apply a sinusoidal on top of that current. And that is used a lot for very low impedance systems. So if you're working on batteries or fuel cells, you're likely to be using galvanostatic modulation, simply because if you're using potential static modulation, it'd be too easy to get current overloads. Okay, that's enough for those questions.
Another question is, in the context of stimulation in plant electrode, can increasing the current cause impedance nonlinearity even for higher frequencies?
Okay. I think I understand the question. If you look at the polarization curve, you can imagine that. So at any point on the polarization curve, you can imagine that if you made a measurement here versus here, these are meant to be vertical lines, that what constitutes linearity might differ. But what we're doing is at that value, we are perturbing around of that value. So we're going back and forth around that. So really, where you are on the polarization curve can influence what constitutes a perturbation amplitude that gives you a linear response. But you're not going to see nonlinearity simply because of the steady current. Does that make sense? Well, to whoever asked the question, I hope that helps.
All right, another question. I'm working on photoelectrochemical water splitting and noticed that literature uses different equivalent circuit models for EIS, often a modified Randall circuit with a CPE, while others use alternative models. How can we determine the most appropriate equivalent circuit model for a given system, and what criteria should be used to validate the fitting? Thank you in advance.
What I like to do is really focus on the physics and chemistry of the system you're trying to study. The approach I showed you, and I know it was really fast, and in 45 minutes, we really don't have a lot of time to cover everything I'd like to cover. If you go to our book, we do cover a lot more different kinds of mechanisms. But you can, if you start saying, okay, these are the reactions that are taking place, and in your case, very often, you have other kinds of modulation that you'll do. For example, if you're studying photoelectrochemistry, it's not so uncommon to modulate light intensity and things like that. So even though that's different than what I'm showing here, the approach that you would take for developing a model is very similar. What I like to say is I like you to start with thinking about what reactions are happening and then building a model based on those reactions. It's very common for people to start with the electrical circuit and then try to understand what the circuit is telling them. And I think that it's a more robust way to start with the reactions and build a model which can be expressed as an electrical circuit. So that's the approach that we take. And then, the circuit that you develop, is not unique. And so it'll suggest other experiments that you could do to help either support or disprove the circuit that you have. And I have found that to be a very useful approach. I think that question may require more of an answer, but that's all I have right now.
I think that was a great answer. Another question is, when discussing how to correct for low current, and they reference slide 27, what range of current counts as small?
Number one, the instrument that you have has specifications for how much current they can measure. So what you'll see is that when you're measuring a high impedance system, the current that you actually measure is going to be very small, simply because of the high impedance of the system. And usually you'll be controlling potential there. If you're looking at low impedance systems, then the current will be much larger. This bandwidth thing that we're talking about, maybe I will take a moment, because this is something I learned very, very recently. But if you look at the impedance response, so if I plot a Nyquist plot here, what we were seeing was something like this, where the impedance would look fine, and then it would jump like this, and then it would jump like this. And this jump that we're seeing here was because we had moved to a different bandwidth, a different current range, at the point that was optimal for if we were using just the cables that came with the instrument, but we weren't. We were using the cables that came with the instrument that were connected to a junction box that had lots of little wires in it and had its own capacitance. And so we had to basically change the frequency at which we jumped to a different current range. And when we did that, we were able to get a nice smooth result. So that's something that I learned recently. The learning curve never stops. I don't know if I came close to answering that question, and if I didn't, you can send me an email and I'll try to figure out a better answer.
I like your use of drawing out the figures on your slides. I think that is really helpful, especially with these complex concepts. Another question someone asked is, have you used the distribution of relaxation time, DRT, for the fitting of EIS data? Sometimes it gives you some extra peaks that cannot be interpreted by the equivalent circuit model. What's your experience with DRT techniques available in the market right now?
Okay, we published a paper on it, and this is my take on DRT. DRT can be useful. Think of it as a preliminary analysis, not as a final analysis. It'll give you peaks. And, the attraction of it is that it looks like chemical spectroscopy. So you say, well, I have time constants and there's a peak here, a peak here, a peak here, and it looks great. But the problem is that those peaks do not necessarily, where the mistakes are made is when you say, I have these peaks and this one is mass transfer, this one is the Faradaic reaction, I don't know what that third peak is. And the problem comes because DRT is effectively using a model for your data. And remember the elephant. Models are not unique. So if your system followed the model that is used by DRT, it'd be perfect. You could use those time constants and say that's what is happening in my system. But if your system is different than the model used by DRT, and in almost all cases it is, then it gives you misleading information. So I see it as a preliminary analysis. It can give you a sense for whether you satisfy the Kramers-Kronig relations. It can give you a sense for how many things you should be looking for in there. But, if you have, for example, a distributed time constant behavior, like a Warburg impedance, that will show up as multiple peaks. And so then you have to understand what those peaks mean. An alternative, if you want a preliminary analysis, I like our measurement model approach better, primarily because it also gives you the error structure of your measurement, which DRT will not do. But maybe we can put a copy of the paper. The paper is published in open access, so we can put a copy maybe in the website in your it's something that's to be available to people, because I think it's important to understand that the problem with DRT is that it assumes a model. And the other problem is that very often people who use DRT will tell you that it's model free. And it's only because you haven't thought about the model. It's not because there isn't a model that you're using. You're using a model. Model is not unique, and other models may describe the system differently. And the question is, what is going to give you the information that you really want?
Yes, I think that adding that publication to the reference list would be really helpful for that. And so one more final question that we have, can EIS be used for modeling a black box without any prior information about its properties?
I guess the question is, what do you want? Do you want to know what's inside the black box? I mean, in a certain sense, that's what we're doing. And then I'd be thinking, it's an interesting question. It's posed in a way I've never thought before. So I'm having to think a little bit about this. If I'm picturing my black box, I'm saying, well, what I could do is perturb it by shining light inside the box and seeing if there's a photocurrent. Something like that. I'm picturing that I would try different ways of perturbing it, each one giving me maybe a clue as to what's inside. If you want to ask, well, here's my impedance response, and can I compare it to a table of known impedance responses? I would say no, you cannot do that. That was a fever dream back in the 80s. That you could do the same thing with electrochemical impedance spectroscopy that you can do for chemical spectroscopies. Have a library of functions and compare against that, and that tells you what's inside the black box. That doesn't work. So I think that what I'd be doing is finding every possible way of perturbing that black box to try to get information about what's inside. I'll think more about that question. It's an interesting way of thinking.
Excellent. Yeah, I thought that was a fun one, and that would be a good one to end on.
You did that to me. Okay.
And so yes, that brings us to the close of today's session here. Let me share my screen just so that I can make sure that everyone has all the information for next week. But yes, thank you everyone for coming today and enjoying this wonderful lecture. If you are registered for the series, you will get a reminder about next week's session. It's going to be on Wednesday. It's going to happen at the same time. And then today's session, like last week's session, it is recorded. It is available on Spotify, on YouTube, on Mark's website. And so we will be sending out links for those. But yes, thank you so much, everyone. Thank you, Mark, for all of this wonderful information. And we have recorded all of the questions that were asked. I think there was a total of about 55 in this session. And so we are going to be posting those as soon as we have answers for them. But thank you, everyone.
Thank you.